Previously, we heard about the intuition, and now we'll see how intuition fails in high dimensions. Generalizing correctly becomes exponentially harder as dimensionality. There is a number of features become large. Machine learning algorithms depend on similarity-based reasoning, which breaks down in high dimensions as a fixed size training set covers only a small fraction of the large input space. Moreover, our intuitions from three-dimensional space often do not apply to the higher dimensional spaces, so the curse of dimensionality may outweigh the benefits of having more features. Though in most cases, learners benefit from the blessing of non-uniformity, as data points are concentrated in lower dimensional manifolds. Learners can implicitly take advantage of this lower effective dimension or use dimensionality reduction techniques. Theoretical guarantees are not what they seem. A common type of bound common when dealing with machine learning algorithms is related to the number of samples needed to ensure a good generalization. But these bounds are very loose in nature. Moreover, the bound says that given a large enough training data set, our learner would learn a good hypothesis with high probability or would not find a consistent hypothesis. It does not tell us anything about how to select a good hypothesis space. Another common type of bound is the asymptotic bound, which says given infinite data, the learner is guaranteed to output correct classifier. But in fact, we never have infinite data, and data alone is not enough. So theoretical guarantees should be used to understand and drive the algorithm design and not as the only criteria to select algorithm. Feature engineering is the key. Machine learning is an iterative process where we train the learner, analyze the results, modify the learner data, and repeat. Feature engineering is a crucial step in this pipeline. Having the right kind of features, independent features that correlate well with the class, makes learning easier. But feature engineering is also difficult because it requires domain-specific knowledge, which extends beyond just the data at hand. More data beats a cleverer algorithm. As a rule of thumb, a dumb algorithm with lots of data beats a clever algorithm with a modest amount of data. But more data means more scalability issues. Fixed size learners, called parametric learners, can take advantage of data only to an extent beyond which anything more data does not improve the results. Variable size learners or non-parametric learners can in theory learn any function given sufficient amount of data. Of course, even non-parametric learners are bound by limitations of memory and computational power. Learning many models, not just one. In early days of machine learning, the model or the learner to be trained was predetermined, and the focus was on tuning it for optimal performance. Then the focus shifted to trying many variants of different learners. Now the focus is on combining the various variants of different algorithms to generate the most optimal results. Such model ensembling techniques include bagging, boosting, and stacking. Simplicity does not imply accuracy. Though Occam's razor suggests that machine learning models should be kept simple, there is a necessary connection between the number of parameters of a model and its tendency to overfit. The complexity of a model can be related to the size of hypothesis space, as smaller spaces allow the hypothesis to be generated by smaller, simpler codes. But there is another side to this picture. A learner with a larger hypothesis space that tries fewer hypotheses is less likely to overfit than one that tries more hypotheses from a smaller space. So hypothesis space size is just a rough guide towards accuracy. Domingos conclude in his other paper that simpler hypothesis should be preferred because simplicity is a virtue in its own right, but not because of a hypothetical connection with accuracy. Representable does not imply learnable. Just because a function can be represented does not mean that function can actually be learned. Restrictions imposed by data, time, and memory limit the functions that can actually be learned in a feasible manner. For example, decision tree learners cannot learn trees with more leaves than the number of training data points. The right question is to ask whether a function can be learned or whether a function can be represented. Lastly, we talk about correlation and causation. Correlation here in machine learning, correlation does not imply causation. Correlation is nothing but two things are related to each other. If one occurs, the other two things simultaneously occur, that is correlation. And causation is if one occurs, then the other should also occur, or the second thing is occurs because of the first one, that is causation. So correlation may hint towards a possible cause and effect relationship, but that needs to be investigated and validated. On the face of it, correlation cannot be taken as proof of causation. Thank you. This is the end of the presentation.